Hello, everybody. Is it okay to start? Okay. My name is Andrei Costin. I hope we met yesterday at my talk. If not, hello again. Before I start, if you want to also exercise during the talk or maybe after, here are some links. You just go to ac.defcamp.dev.camp and you'll download a virtual machine which I'll be showing and the exercises. So basically it's kind of a workshop style. I'll just show you the demos, but you can also take them and do exercises for you. I'm not sure how long they'll be here because it's on DefCamp infrastructure, which I want to thank DefCamp and Andrea Vadani for helping setting this up and giving you the opportunity to download them. So just go ahead and grab them and distribute to your friends and so on. Okay, and so this second talk I'll be presenting you hacking and securing network monitoring systems, and that's kind of a mixed talk where I just give a high-level overview on these systems, and I'll do an end-to-end walkthrough example on Ganglia. And I'll present what is Ganglia as well. So a short who am I, but I'll not spend time on this because we are a little bit delayed. So I propose the following agenda for this presentation and this workshop. I'll just give an introduction, an overview. We'll just go very quickly on the attack lifecycle, how the attackers do the network attacks in general. Of course, static and dynamic analysis, one of our favorites. And a little bit of vulnerability analysis, how to actually discover vulnerabilities or how to actually analyze and do some exploit development. It will be a very simple one and very short one, but if you're not very familiar or you just know the theoretical part, I think that could be very interesting for you to have a hands-on exercise, which you can also do yourself in the virtual machine afterwards. So just a small introduction. What is cloud computing? Because cloud computing now is a very, very hype concept, is a very hot topic, everybody's crazy about it, and suddenly we are investing so much money in security in cloud computing. But essentially, like for IoT, the backbone of our IoT are the embedded devices and the insecurity of embedded devices. The same thing applies to the cloud computing because there's a very nice paper, if you go and look it out, Exploiting Cloud Utility Models for Profit and Ruin. There's a very interesting thing which says when broken down, cloud computing is a specialized distributed computing model, nothing new. So it builds upon the desirable characteristic of cluster, grid, and utility systems. So you know all these old academic and research HPC, high performance computing, clouds, basically multiprocessors and distributed computing systems which were not very popular except in a few research centers. And I remember I used to hate them because they were not so well integrated and not very fun to play with. Now they are becoming more attractive because cloud computing is building upon them with more nice features, APIs, and scripting capabilities. So it's much more sexy than, let's say, 10 years ago. So essentially, the cloud computing is basically a paradigm, an API, a framework, some interfaces on top of very simple and old high-performance computing clusters and grids. So what are these? These are basically, you can see them as multiple racks or a single rack or like an array of racks spread in a data center or multiple data centers. And usually, the high-performance computing flow is something like you have, for example, you have the HPC clusters and servers and some other clusters which communicate over fiber optics or whatever other channels. And then there's some other equipment, like, for example, it can be the Large Hadron Collider data acquisition, which pumps terabytes of data per second, or it can be any kind of physics simulation, Big Bang simulation, and so on, or like genome coding, human genome coding. So there's usually a large amount of data which goes from some physical process or some simulation which goes into the cluster. And this cluster is supposed to parallelize and crunch all this data so you can get the results very fast. You cannot wait for a billion years to find if there was a Big Bang or not. But more importantly, from our perspective, is not to secure everything here, because usually it's like one piece of management which goes. But we can see that there's some local researchers and analysts who need to somehow connect to the HPC and do some tasks. And there's also some remote researchers, because usually the research or the cloud computing is distributed. You have a colleague in Hong Kong, one in the US, one in London, and you want to collaborate. So of course they'll connect through internet and some kind of one interface to the thing. Now we have all these, but you can see there's a lot of complexity, like a lot of small pieces which compose the HPC, the physical things, and then also the users. And all these interactions and pieces of cloud computing or HPC systems have to be monitored. Because if you have two computers at home, you can basically monitor them by hand or with simple scripts. But when you have thousands of workstations spread around the world, it's similar as enterprise infrastructure. You want some unified console or unified approach to monitor these kind of systems, whether a node is healthy, whether your Large Hadron Collider sensor is working okay. So you need some kind of monitoring. And usually this monitoring, I mean, many times this kind of monitoring is achieved using NMS, which stands for Network Monitoring Systems. And I think it's a little bit misleading, because usually these tools are not only for network monitoring, because it just doesn't monitor the fiber links and the state of the network. It also monitors the health of the node, the CPU utilization, the memory, the users, the processes which goes on, so that they can optimize the high performance computing utilization, and also detect the faulty nodes and basically distribute or migrate the processing task to some other node. So this kind of monitoring systems is kind of a middle layer between the system admin users and the physical network or the virtual networks. And they're used very much in high performance computing, in grids, clusters, or federations of clusters, and of course in the cloud. And the idea is that the NMS, what it does is a very simple architecture, or a very simple idea. Is basically you have a core node which essentially collects the data from all the smaller nodes which transmit monitoring data like CPU, power usage, RAM, hard disk, network status. And all this monitoring data is being pulled or being pushed to the main head node. And then this head node provides some kind of interface. And most use case is the web interface, because you don't need thick clients. So everything is in web in your browser. You can connect from any place in the world. And it's displayed in a cluster management interface or NMS interface. And of course, there are like dozens of tools. These are some of the most popular, but there are some in-house developed commercials. How many of you used at least once one of these tools? Okay, so it's like 1/3 for the, okay, 1/2 is okay. So there's different kinds of tools. They have different features, different pros and cons. Some people use a combination of these because they can get more efficient by using two of them, or they use them as a complementary or as a backup. It doesn't matter. In the end of the day, the idea is that one of these tools will be present in one of your, let's say, high-performance computing infrastructure or in your data center. And in our case, we did a study which was a little bit backwards. So we, just to give you a little bit of a back in time, we started finding some interfaces which openly distribute or open the interface of Ganglia and Cacti and Observium on the internet. And it was kind of expected and unexpected, because the idea is that, yeah, it's a monitoring interface. You cannot do much management because it's not a management system, it's a monitoring. But the idea is that it leaks so much information that can help the attacker, and sometimes they're also exploitable. So I'll show you the demos and explain a little bit down, but the idea is that we focused on this Ganglia, Kaki, and Observium, and these are the tools you can freely download. They are mostly PHP based on the web interface, and there's some binaries which goes into the monitor nodes. So there's a combination of both worlds. We focused on the web interface because this is what you usually find on Shodan, or this is usually what you find on Google Docs. And I'll show you examples of Google Docs as well. So for Ganglia, I'll focus this presentation on Ganglia, but the same process of thought or methodology can be applied to any of these with some improvements or deviation, but you'll get the idea. So for Ganglia, for example, there's the head node is, let's say, here, and there is Ganglia meta daemon. Basically, it collects the, and this picture is not mine, it's copyright for somebody else, and I stole it shamelessly from the Google, and I thank you for of the author. But the idea is that there is a head node which collects the metadata from all the small nodes, and here are free, but usually you get hundreds or thousands of nodes. And all of these nodes, they have a configuration file which says which kind of metrics to collect and so on. And these metrics are collected by Gmon daemon. It's basically Ganglia monitoring daemon, which is on monitored nodes. And they just push or pull the data into the head node. And there's a lot of things going on here, but I'll not focus. The interesting things goes here because this is where we usually the easiest and fastest attack surface goes, where you do man in the middle of a browser, you do a phishing on a system administrator, or you just find these systems on the internet and you can just go to their Apache interface and work your way through here, and then if you're here, then you can take the nodes as well. And I'll show you like example where like a simple PHP vulnerability allows you to just go and take over the entire HPC cluster. So I put small exercises, and you can download them again. I'll just ac.def.camp. So if you're doing so, somebody is doing this, succeeded? No? Yes? Okay. So this is the exercise for setup, because everybody is very technical here. I'll not go too much into it, but I'll just, I'm sorry for the funky icon changer. I know it's a little bit confusing. So we have the setup where, well, there's nothing fancy. You just install the Apache and the Ganglia. It goes pre-built into the Ubuntu distribution, and then it just gets installed into your local host. And the idea is that you can then just go into the web interface, and if you look at the local host, is basically see that we have unspecified cluster because I didn't give it a name, and it's only one node cluster. Basically, is a cluster of one node which is being managed by this interface, and you can see that it's this virtual machine interface. So I can go here, and you'll see that there is a lot of information displayed, like the host overview, the internal IP addresses. But if you go to the host overview, you'll also see things like, okay, the internal IP address, the Linux kernel, or the whatever operating system details. So the idea is that there's a lot of information which an attacker can get from this kind of interfaces, right? They don't need to proactively come and scan with Nmap your infrastructure. They just go and collect this information from the internet, and I'll show you how easy it is. And the idea is once you get the internal IP addresses, you basically know the whole network, you know their OS kernel versions, and if you have a CVE for that OS kernel version, it's like, bam, you're there, right? You don't need so much things. Everything is automatable. And so this is a simple interface of Ganglia. Then what there's a lot of pop-ups, sorry for that. So there are two users on this virtual machine. One is the CloudSec, which is, let's say, the cloud security administrator, which is using, and one is the attacker. And for the attacker, I'll go in the end. So normally, if you set up your Ganglia as specified here or any way you like, you can just check that the password is the same as the user, so there is no. Yep. So you see that for this, because this is also the head node and also is the monitor node, you can see that there is a meta daemon which runs on 8651, 8652, and is also a monitored node. It has the monitor daemon which runs on 8649. Why these ports are important? Because you'll go to Shodan and basically you'll find, by checking these ports, you'll find like a lot of interesting, like tens of thousands of them open this port like on the internet, and it's XML, you can process it. So the idea is that, yeah, we can connect to the meta daemon of this head node, and you see that it's XML, and it basically gives you all the values and the metrics and so on. So you can easily build some scripts which automate all this data collection and processing, and then once you know, oh, it's a kernel this version on this IP, just send the exploit, bam. Okay, this is the setup, is easy. I'll not try not to spend too much time on this. So the idea is that why Ganglia is important, for example, personally for me, if you go to Ganglia, is kind of old project is, I think, one of the first to do. And if you see who uses Ganglia, it's like, oh, like Twitter, Flickr, Microsoft, HP, Cisco, CERN, Lucent, I mean, US Air Force is like, oh my God, everybody is using this, right? And there's like, and thousands of our people who just are much smaller but have much interesting infrastructures as well. So you get the idea that once you're in an internal network and you see a Ganglia interface, or if it's by mistake exposed on the internet, worse, then you can see that, oh, there's an interesting stuff to collect and also maybe to exploit for an attacker. So maybe you want to defend. And how can somebody tell me what is the first step in an attack life cycle? So for example, there's an attacker and they want to attack somebody. Recon, exactly. So what you do is you do the initial recon. You need to collect all the information about your target or their target, and they need to collect all the IP addresses and versions and so on, so they can build a very good profile and basically fine-tune the attack so it's 100% succeed. Then goes the initial compromise, which can be like a simple remote code execution, maybe not as a privileged user, and then you use a kind of, you establish the foothold, you put something there, and you also elevate your privilege, and you just try to establish the foothold, and then there's a whole circle going on, like you escalate the privilege, you do the internal recon. This thing can, some of these internal recon and initial recon are some steps which can be optimized using the exploits or the vulnerabilities or misconfiguration of these kind of NMS tools. When you move laterally, basically it means that once you know the IP addresses of all the small, like 1,000 virtual machines or physical nodes in the system, you just send your kernel CV exploits to those internal IP addresses, and you maintain presence. You basically take the whole infrastructure. So the idea is that one of the attack types on NMS is the information leakage. As you could see, I mean, here a lot of informations about the nodes, right? So sometimes they also get a location. You see the uptime. Some of these are not rebooted or updated for hundreds of days, and the kernel is very old, so it's a very good target. And they cannot reboot it because maybe it's running like a, I don't know, genome decoding process for 2 years, because it's just like that. It takes time. And they cannot just reboot it because there's a, I don't know, kernel patch and take over again. So you get the idea that there's a lot of information, and I'll show you a little bit more, but it basically helps the attacker avoid active scan, right? He doesn't need to be very noisy. It's a passive scan. You just go on Google, you get the information, and you get everything. You don't need to ping and nmap and send a phishing in email and establish foothold and then basically show your mission. Then there's web application security that, as I mentioned, there's the web interface and the backends. So backends more or less are secured and can be secured or more or less. But the idea is that usually the web application security, from what we've seen for the last decades, is that web application security is still hard, right? I mean, it's 2015, you still find XSS and SQL injection. So it's like, and despite all the tools like static and dynamic analysis and this and that and all the marketing, there are still vulnerabilities in web applications. Because web application is not a trivial problem, even though it seems, and academics in industry cannot solve it easily. There is no silver bullet. So you can still get XSS and SQL injection and remote command or code execution. And it is basically used to establish the foothold. And I'll show you how an attacker can just get execution of code in using the ganglia. Then there's classic attacks which can be used. We didn't investigate, and I'll not present this, but yeah, basically you can find buffer overflows in the backend using any methodology you like. You find kernel exploits or you reuse existing ones. And this is, of course, used to escalate your privilege because maybe the web interface is running as nobody or www data, but then you maybe all want to run as a root. And usually all these daemons have to run as root because they need to collect like very sensitive pieces of information about the state of the nodes. And the idea is that they need some kind of a elevated privilege to collect this information. And then the idea is that the information leakage also is not useful only for recon, but is also used for mimicry and blended attacks. Because if one of the steps in this is to maintain presence. What it means is, it sounds easy, but then if you're too noisy, you're detected by IDS, IPS, or just a simple log review, or the attacker is detected because they are just too noisy, right? So you have, usually the attackers, they have to avoid this detection and maintain presence with this. And to maintain presence and avoid detection, basically there are class of attacks called in academia mimicry and blended attacks. Basically, the malicious processes, they mimic the behavior of normal processes. Maybe they mimic their name with a small misspell, or they just mimic the CPU usage and network usage. And also the blended attack is the same. So it's kind of, they are different attacks, but they are interchangeable. You can combine both. So the idea is that the malicious process just blends in and mimics the normal usage. And it uses all the info leaks, because if you look into these details, you can see that there's all the information needed for establishing a baseline and then use this as a mimicry attack. Because if you know that at this time there's a process called blah, which uses 95% of CPU, maybe you can do your denial of service or all these things exactly at the same time. So you blend with normal CPU 95% usage. If you do your CPU, like denial of service attack right here in the middle of the day where there's nothing, then it's easy to spot because it's anomaly. So this kind of information can be easily used for mimicry and blending attacks. So the attackers can maintain presence. Then there is also the usernames leaked in some of these interfaces. And let me just try to find. Okay, in this one I don't have, but I'll show you like a very interesting example from Romania. The idea is that this interface also leak the usernames which are logged into the system, and basically it's a PS in the web interface. You see the processes names and the users who run them, and once you know the username, you can try to brute force their passwords, or you can try to use them as sending a phishing email to get their credentials and get deeper and deeper into infrastructure. So one of the tools people use for this kind of things are the social engineering toolkit, where you can have different kinds of web mimicry and valid email looking things. Now, for the CVEs, for the kernels, is that if you go to the CVE details or you go to NIST NVD database, you'll find that there's a lot of kernel versions, kernel branches, kernel modifications, and so on. And you can see that many of them have like hundreds of vulnerabilities. Of course, not all of them are like elevation of privileges, and not all of them are remote code execution into the kernel. Some of them are denial of service, but still with a denial of service, if you have like, there's an important cloud provider and you can get through the monitoring system into the thing and then use a denial of service exploit on those kernels, just bring down the entire infrastructure, and this can be played in different ways. That's why it's important to keep in mind this number of vulnerabilities. I mean, and then if you go for particular versions, you can have basically the split, and some of them also have the exploits available in ExploitDB or other places. And you can basically just take them and test them. And you see that most of them are denial of service, but of course you have also overflows, which can, with some degree of success, be turned into code executions or other stuff. Memory corruptions, and like other information leakage. So there's a lot of places where this kind of kernel information thing can be used. I think you know this very well. Then, yeah, the mimicry and blending attacks I already explained. So basically, if you have a CPU and memory and network traffic usage, you can just perfectly blend in by collecting this data every day and then building a baseline. And then you want to minimize the deviation of the malicious activity from this baseline. And this is basically formalized by this, but this just is a formula. You want to deviate as minimally as possible from the learned model of this particular node or this particular infrastructure. And this information, as I said, can be obtained via active reconnaissance, where you just take the Nmap, Amap, Nessus, Zmap, and just flood the network. And okay, there is some things about this. I mean, this can be useful as well, but sometimes they are noisy and sometimes they are not so accurate because it's kind of a black box testing, right? You don't know what's the blocks behind them, but you try to use some kind of information from Nmap, and it says, yeah, maybe it's a Linux kernel version 0.2. But using passive and cooperative information leakage, where the node gives very authentic information because it runs at high privilege, you know exact information. You don't need to take guesses. It gives you the exact kernel version, it gives you the exact IP address, and that's fine. I mean, you don't have to do any job. And some of these you can find with simple things like that, like Google Dorks. And you'll be surprised how many of them you find. For Romania, for example, you just do this, and we can quickly try to do this. Sorry. So you see that there's like some some physics department, some space science, and so on. I'm not saying go ahead and smash these guys, right? But if you know them or you have a point of contact, please drop an email. I really don't know every one of them because we found thousands of them, and sometimes you don't know the web administrator or the admin. But if you know one of those guys, just drop them an email and say, hey, maybe you want to take out this interface or patch it and so on. And you see, I mean, I'm not going to open these links, even though there is no password and you can go and freely see, but you see that there's the CPU usage and load distribution, and there's triple dots. So if you go and see the cached version or even go to the site, then you'll see that there's all this information I was telling you about. So it's really interesting that this kind of things land up on the internet. But I mean, you can do this kind of variation. You go to edu, and I mean, there's multiple ways you can get information about. You see, there's thousands of these kind of interfaces being on the internet. So one particular example is, yeah, as I told you, some of these interfaces, they show, I'm not sure how many of you can see, but it's kind of a PS, and you can see that there's some root users and there's some UNL users. So if you know UNL, and maybe you know his birthday in that particular university, maybe you can brute force his password. And yeah, so the idea is that you get all this IP information and so on, the exact kernel version. Then there's some other example for Cacti. And basically, Cacti is similar to Ganglia. And the idea is that you get the same kind of information. It looks something like that. Nothing particularly very much different. You have the nodes, you have resource utilization, you have some reporting, and so on. But the idea is that sometimes these kind of systems, they also have both of these interfaces. So for example, we found this, for example, there's a university in US which gives this Cacti web interface, and one of the nodes has a public DNS name like aglt2.org, let's say. And then you go to aglt2.org, or let's say you can script it very easily. I mean, there's no rocket science. You just script it. I'm showing you manual things, but you script it. You go to aglt.org with a crawler. You crawl all the things. One of the links is job status page. When you reach this, there's some other links, and then you reach a Ganglia interface. So you see that from one interface you can link or find automatically some other network monitoring interfaces. And basically, you can even build more information and find even more nodes and more interconnections, because sometimes some interfaces are kind of complementary and they manage or monitor different parts of the cluster. So yeah, from Cacti you can reach Ganglia, from Ganglia you can reach Cacti, and so on. For Shodan, for example, I'm not sure you can see very well, but I'll tell you that it's a filter for Romania. And this is the port 8649, which is a Ganglia monitoring daemon. And you can see that there's quite some results which publicly expose this port on Shodan. So what it means, you basically can just go with Telnet or Netcat to these ports, and you get the XML information just like this. And it's like all automatable. How to create these kinds of dorks? I mean, you can try manual things. Another thing is you can try to derive it from a valid Ganglia installation. And one of them is just you check your I mean, it's not rocket science, but again, it's a good exercise because you understand. If you get the index page of your Ganglia installation, for example, you have a Ganglia installation in this virtual machine in your test, and then you grep for Ganglia or for various keywords, you get some particular types of strings which are good indication that you might find these strings also on the internet using Google Dorks, like in text or in title, and there's other keywords. So if you look for RRD tool version 147, then you can find some other systems and so on. So you get some key search terms which you can use in Google Dorks or in Shodan, and you keep finding more information like that. Because yeah, I used the cluster report, but then you can also use, for example, this one. Just as an example, and we use in text. Oh, see, they know I'm doing funky stuff. So you see that, oops, there's some other Ganglia reports, and this is basically something you can build up. You can build up a search dorks dictionary in this way. You just install the system you want to monitor, you extract the keywords using simple greps and simple things, and then you just keep querying the internet, and maybe you find something, and you find a lot. 1, 2, and 3, basically all over the world, and I'll give you some examples on the numbers. So this is kind of the how to create this kind of dorks. It's not rocket science, and if you see these dorks, it's like easy to create, and it's just you need to install them to be able. Now, as a result, what we've been able to do is that we found at least 300, almost 400 Ganglia head nodes. And then we parsed all this information because it's publicly available. It's not requiring any password. If it requires any password, we just don't look at it, and that's it. So Ganglia information, they exposed around 43,000 internal nodes, like internal IP addresses, sometimes connected to their public DNS names, and they expose all these kernel versions. And we try to kind of combine and see how many clusters and grids. So there are some statistics in the paper which you can find at the end of the presentations. Then we also found around 5,000 CACTI web interfaces, but around 80% of them, for both CACTI and Observium, they used at least HTTP basic authentication. So it was, let's say, more or less secure. It's not good to try like random passwords on other people's infrastructure, but at least they did something, or the latest version require a password by default, where, for example, for Ganglia, they didn't require any password for anything, even in the latest version. So we also try to see by country which country provide most of them, and there's US leading with China. Apparently they have a lot of research going on, and for some reason, they also don't secure these kind of monitoring interfaces, which is bad. Then we also try to see the kernel versions. I mean, if all the nodes in these discovered online systems would be latest versions, would be fine. But of course, there's a great spread of kernel versions, and there we found a big number of 120 main kernel versions. And the kernel version 2.6.32 was basically one of the most popular. It ran on almost 40% of the internal nodes we discovered. So if you take this number and you just focus on exploitation of 2.6.32, which, well, have some updates, but I think is not so maintained or something like that anymore. So you can see that you can customize some exploits for 2.6.32 or find new exploits, and you'll have like 40% of nodes like in one go, because it's one version, one main version. And interestingly enough, we found that only 9 nodes, like not interfaces, but 9 nodes, they run the hardened sources or GR security patches, basically bringing some extra security features into the kernel. And it's a very small percentage from 40,000 nodes. Also find Amazon kernels, and these Amazon kernels are indication that they're running inside some virtual machine on Amazon cloud, and it was a very interesting example that there was some big vendor production monitoring systems running on Amazon Web Services. And basically, they were like exposing MongoDB and monitoring masters and some internal hosts. And yeah, it's called big vendor name production. So I suppose they use it for production. It's not there anymore, so I guess they kind of realize it's a bad idea. Then we also use the static and dynamic analysis on the web interface. And static and dynamic analysis is a good way to find vulnerabilities in both interpreted languages like PHP and Perl, and is also good to find vulnerabilities in binary code or source code. So that's a normal thing to do. So we use RIPS for Ganglia frontend because it's PHP, and for dynamic analysis we use the Arachne scanner. Basically, it's a penetration testing tool. And we tested like 25 Ganglia versions. You can find them inside the virtual machine. And 35 CACTI versions also you can find inside the virtual machines. And the interesting idea is that in academia it's always interesting to follow, or is kind of required to follow a kind of strict methodology where you see that there's a correlation between some events. You cannot just say random facts. And interestingly enough, for example, this is the graph of is the graph for static analysis for each version. So basically version 2.0.0, 2.1.1, 2.1.2, and so on. And this is basically the distribution of different kind of vulnerabilities. We can see that a lot of them are cross-site scripting, so there's a lot of cross-site scripting, and you can see the consequences. You send a phishing email with the cross-site scripting to monitoring admin, and then you get the credentials and so on. But the idea is that you have this kind of a pattern with numbers. Some of these can be false positive because it's static analysis and they require some confirmation. But nevertheless, the idea is that you have this pattern. And then when we do dynamic analysis, you can see there's kind of almost a direct correlation, right? Where dynamic analysis produces the same kind of a curve of number of issues found, where the versions up to 3.3.0, they used to have less vulnerabilities both by static analysis and dynamic analysis, and suddenly from 3.3.0, there was an increase in issues found by both static analysis and dynamic analysis. So it means that there were some modules or some big chunk of a commit which introduced a lot of, let's say, prints or echoes or things like that, which led to this kind of cross-site scripting and so on. And then you can see that from version 3.5.7, they kind of cleaned up the code, they maybe modularized it, they did some security audit, and they actually managed to decrease it. So this is confirmed by both static and dynamic analysis. So what it means is that if you follow a good methodology and you find that different techniques applied to the same things, like the same code or the same devices and so on, lead to the same results, it means that that's kind of a confirmation of what you are looking for. And this is what I advise you to do as well, maximally possibly, to use like cross-correlated techniques. I'll not go well, I can go a little bit on the static analysis exercise. You can find these exercises online as well, so you can do them yourself. But for example, the idea is that with a static analysis, you just use this RIPS tool. We had some wrappers written for them. So if we look, okay. If we look into the Ganglia RIPS, there is no report, and then we'll use this RIPS command interface that will put some reports here, and that will test the Ganglia web frontend PHP files. And you'll see that there will be some parsing of PHP files, and it will take a little bit of time. But the idea is that after it will parse and it will find all these things, you can find the vulnerabilities. And I'll leave it run for a little bit. The idea is that then we'll see that there are some exploits which can be triggered in various modules. And while the static analysis runs, I try to show you the dynamic analysis. And then dynamic analysis is not very complicated. So basically, you have the Arachne tool, which you run on your local host, and you want to run them on Ganglia web interface, and you want to test for XSS or command injection or file inclusion or path traversal, and then you'll see the results. So now the static analysis is finished. Well, it can take several minutes. There is no problem with that. And if we go into the reports directory, then we'll find, for example, cross-site scripting in this file. And these cross-site scriptings or command injection or whatever you're looking for, they'll also be linked to particular PHP files. So one of these files, and I'm running in this virtual machine, at least the time I set up it was the latest version, 3.6.1. And by using this static analysis and then using the dynamic analysis and also manual confirmation, you can see that there would be some kind of cross-site scripting even in the latest version, right? So you see that by using these kind of techniques, you can very quickly find XSS very targeted. And why is because, for example, you can check this file, check multiple metrics in the static analysis report. And you'll see that it appears many times. And we can grab for cross-site. Oh, OK. OK, maybe I'm doing something wrong. But the idea is that you can see that, well, you follow the exercise. The idea is that you can basically correlate with both techniques, and you can see that you can quickly confirm that there is XSS. OK, so I have, I think, 10, 15 minutes like that. Hopefully. For example, the idea is that there is a particularly interesting CVE for ganglia. And the idea is that this CVE says like that: unspecified vulnerability in ganglia before 351 allows attackers to execute arbitrary PHP code. Like arbitrary PHP code is like, oh, you can send any code like system, eval, pam pam, and everything is cool. We are known attack vectors. Why unknown? I mean, why don't you publish? It's open source. I mean, sometimes of these vulnerability reports are very strange because they don't give you enough information to help patch the system. And they're kind of just putting you in a gray area that you know there is some potential PHP code execution remotely, but you don't know how to secure. And interestingly enough, we found this PHP, this version, this particular ganglia web versions before 351. So basically, we count all these, the number of version 2, 2.1, 2.2, and so on. And from 364, we found more than 53% run version 351. What it means is that more than 53% of head nodes allow PHP code execution, and it means you can basically own around 50% of the currently exposed ganglia clusters on the internet. Like in theory, because you get into the head node, you PHP execute, and then you move laterally and so on. And the idea is that how you usually do this kind of how do you find the vulnerability or the attack, the exploit? You do diffing. You do a diff between two files. And it's very simple in this case. I also installed on this virtual machine, and you'll find there is this ganglia front end, which is the latest version, but I also installed a vulnerable ganglia version, which is called the CVE, and you can see that it's version 350. OK, so it should be vulnerable to that CVE and should allow PHP code execution. And what we do right now is, OK, let's do some vulnerability analysis. So I did some of these steps already for you in the virtual machine, but the idea is that I go into the ganglia web. I have all these versions there, you can see. So you can go and play with them. You can also do, OK, I think I'll do like that. So we do like a kdiff, and there's a lot of diff files which have been patched for various things or maybe added some features, but one of them is interesting enough because you have to do some manual or some heuristics, but if you look into the graph PHP, for example, there will be some line which says check for path traversal issue and so on. So there is a path traversal. Oh, that's cool, right? So you check how it was patched and what was the problem. And basically, you can supply some PHP report file. And then if you look, the PHP report file variable is taking the graph input and just concatenates with PHP. But where is this graph? If you look up, then this graph is being taken from basically from the user input, right? So, whoa, we can create the exploit easily. So the idea is that if you can control this graph variable in the post request, and you can have a PHP file on the host machine by an attacker, then you can basically trigger the exploit and so on. So you see, this is a quite simple thing to do. You just put a .php file, and then you put path traversal, and you put in some globally writable. And globally writable usually is /tmp. And how you put a file in /tmp, there's like hundreds of ways to put file in /tmp. You print a file, you send an attachment. When it's open, it's put by the mail client in /tmp. There's like many ways you can actually put a PHP file in /tmp. And now, for example, let's say that we are the attacker. We're connected for the attacker. And yeah, we are this one. And OK. We go to TMP, and there's no such file as etc password, and there's no such file as Ganglia. Then what we just simply do is we try to open the proof of concept. And basically what we need to do is a simple PHP file. And because we can invoke a path traversal, and how does a path traversal look like? We have a graph PHP, which I showed you in kdiff, in diff. And there is this G parameter, and it allows for path traversal, because that's actually what they patched, is a path traversal. And we say, hey, just go here in TMP and take my attack.php, and it will execute, because there was a path traversal. And it will execute this particular file. And here we just do simple proof of concept, where we just touch an attacker and get the etc password. And let's try to see if it works. Hopefully it works, because sometimes the demos are. So we are the attacker. Let's say we kind of attack PHP. And OK, I put it by hand, OK? But again, the attacker can send this TMP file many other ways as input vectors. And what we have to do is just we need to find an interface which is not secured, and we can access the graph PHP. And basically, we try to see if it works. And let's say this is our Ganglia front end, which is vulnerable to this CVE. We found it on the internet. And how do we find them on internet? I showed you with the Google Docs, and you use the version 3.5.0. And the idea is that you try to call the graph PHP and hope it works. It shows some file, and because it's a graphing thing, but it didn't work. So, but maybe it's. OK. Just give me 1 second. I'll try to fix it, but. Oh. OK, so something is wrong, but definitely you can use this, and it's tested to work. I'm sorry for this, but yeah, I'll try to fix it. Nevertheless, it was tested to work. The idea is that you can see that there's like this kind of things. And then there's, OK, the exercise how to secure, but of course everybody here is technical, and you know how to put a HTTP basic authentication and authorization, and how to create an HTTPS configuration. So I'll skip it, but the idea which is interesting is that from all these things we found on the internet, only 11% run HTTPS, and only a small chunk of these which run HTTPS actually run some full trusted HTTPS chains. So some of them are self-signed certificates, some of them are like not trusted chains. So it means that even though there is like HTTPS securing these interfaces is not completely secure and can be compromised with different attacks. I invite you to go and check the paper, and I hope you found this talk interesting. If you have any question, I will be very happy to take them. Or if you have any question about the exercises or the walkthrough, just drop me an email. I'll be glad to answer. And yeah, definitely the proof of concept works. Maybe it's just some configuration things which I didn't encounter, and I apologize for this. But if you get it, I mean, you should get it working. Thank you. Any questions?
Do you have any questions? Okay.
You've said that only 9 hosts were hardened with GR security. Have you checked about C Linux?
No, we didn't check for C Linux, so we don't know because, well...
You should have, because 2.6.32 is a default kernel on some versions of Red Hat Enterprise and CentOS, and most likely they would have C Linux enabled by default.
Yeah, so the idea is that sometimes you just get a generic Linux kernel banner in that thing, and you don't actually know if it's C Linux sometimes, right? So it's a passive reconnaissance, so we cannot just go and actively test, right? I mean, that would be like not very ethical, but it's also was not our purpose. But I agree, yes, there could be some, high chances that some of these or a majority of these hosts run C Linux with this 2.6.32 kernel, and that's a good remark. Yeah, thank you.
Any other questions? Okay.
Okay.
Thank you, Andrei.
Thank you, everybody.
Okay, next, Mohamed Bedoui is going to take things from where he left them in the morning during building a weaponized honeypot. This won't take long. We will come back right after. We will continue with Rogerio Winters, okay? Thank you.
Yeah, so there was a very good comment, and basically it didn't work because the Ganglia attaches .php extension by default, and I named the file attack.php, and when you have another PHP, then it's a different file. So basically you create the file without the PHP extension. It's like tmp attack, and then it's like that, okay? So thanks for the comment.